Hi and welcome everyone. In this video, I want to go over the volumes by cylindrical shells. So let's kind of see what is a cylindrical shell. Cylindrical shell, you can see the picture is here, but is a hollow cylinder such as one shown below. So we're talking about that. The outer radius of the shell shown is R2. It's that one. And the inner is R1. So it's that one. I think it's pretty straightforward. Since all cross sections of the shell are the same, the volume of the shell is the area of the base times the height, h. And this is the height. So if we write that formula, first of all, let's go over the area. So the area is going to be pi r2 squared minus pi r1 squared, but we can use some algebra here. We can take the pi out, factor out the pi, and then factor r squared minus r2 squared minus r1 squared. So that's the same as r2 minus r1 times r2 plus r1. Now, what we can do is multiply and divide this the numerator and denominator by 2. So, and there's a reason to do that. We're gonna see why. So if we do that, then we get 2 pi times r1 plus r2 divided by 2. Again, here we can cancel the 2's. We're just multiplying the 2 to make our job easier. What is r2 plus r1? It's r, or you can see sometimes they say it's r bar, which is the average radius. And what is that distance? That distance is just from the center to the middle of this section. R2 minus R1 here, we can call that delta R, and that's just the thickness. So, and let's see, it says here where R is the midpoint of the interval R1, R2, and delta R is R2 minus R1. Therefore, we have the volume of the shell shown below. So the volume is just, we can take that and multiply it by the height, and that's how the volume is present. Now let's see how we can use that in calculus. Here, there another way of showing this is exactly the same thing. So let's say, well, the delta V is just, the V is going to be the perimeter. So perimeter, which is 2 pi r, 2 pi times radius times the height. So the height, we saw that's the height, and times the thickness, where in this case we call it delta x, but that's the same thing as delta r here. When we deal with functions, we use delta x. And let's understand that, just remember the height here is our function, f of x. So, and of course the perimeter is 2 pi x. Now, if you want to find the volume, well, let me go over this, then I'll come back and show you that formula. Let's see, we have a function here. This is our function. So y equals to f of x. We revolve that about the x-axis. So x-axis is the axis of revolution. Now, this x star I, which goes from the y-axis to the middle of this thickness, and that's, we can call that x star I. And this one is x star I minus 1, and that one is x star I, and this is right in the middle. So this is basically the radius. So again, from the middle of this rectangle to the axis of revolution. Here, axis of revolution is just y, so we call it x star I. And the height of course, is that, and that's just our function, y equals to f of x. This is another way of looking at it. So we take a piece of that function, which looks like a cylindrical shell, and what we do, we revolve it about the y-axis. So now in this case, again, this is our function. That's the piece we took and we're revolving it. So let's understand. Now, if you want to take the integral, well, what we can do is just find v sub I, the volume of that, all this solid, and then start adding. And then when I say start adding, that means we are going to be using the Riemann sum. And of course, then changing it to an integral notation. So we are going from A to B. See what we need. We need the height, which is our function. And here I put it f of x. So the thickness is delta x. And of course, the radius, which is going to be this distance. And it's shown here also. Now, when you solve a problem like this, main goal is to find the radius and the height, then you can set it up. So now coming back here, I put the volume is going to be the sum going from, or the integral going from A to B, and we do have to find A to B also. 2 pi x, and 2 pi x is the circumference, then times f of x. F of x is the height of the solid, and dx is the thickness. X, I put, this is the distance from the middle of the shell to the axis of revolution. So be patient. Once we do example, this is gonna make a lot of sense. Now here I have some summary for you. The volumes, again, you can start with pi r1 squared h minus pi r2 squared h, as shown in the figure, the first figure. And you can say, so there's an h missing here. So let me just add that. So if we factor out h and r, so we have pi times r squared, r1 squared minus r2 squared, that's part times factor that r1 plus r2 times r1 minus r2, and that's times h. Then again, I'm just repeating myself, you can multiply top and bottom by 2, and you get that expression. So basically what we have is 2 pi times h and times delta r, which is the thickness. And again, what we're missing here is an r, so it's 2 pi times r. Let me fix that. So 2 pi times r times h and times delta r. So 2 pi, r is the average radius, h is the height, and of course delta r is the thickness. Now, that's the volume again of this piece that we are revolving, but we have to add all those. So the volume is going to be, we can use the Riemann sum, limit as n approaches to infinity of 2 pi x star I times f of x star I times delta x. And that's just another way of writing the Riemann sum. And if you change it to integral notation, so that's going to be the integral going from a to b, 2 pi x f of x dx. And this is when revolving the solid or r about the y-axis. You can have the same thing we learned in the last lecture, that you can revolve it about the x-axis. So the notation changes. Basically what you have is 2 pi y gy dy when it's revolved about the x-axis. Little note here, the radius of the shell or the average radius is different when revolving r about x equals to a and y equals to b. That's not when they're not the x-axis and the y-axis, and I do have an example. I think the example will clear this out. I chose some example here for you, and I went over all of them. So let's solve some problems. The first one, it says find the volume of the solid obtained rotating the region about the y-axis. So very important. Bounded by y equals to 2x squared minus x cubed and y equals to 0. Now I have the graph here for you. If you graph that function, this is our function. So again, if you take a section of that function and start revolving it around about the y-axis, let's see what we have. We need the radius, which is x. Again, it goes from the y-axis to the middle of this rectangle. This is the height. The height is just our function. So you can even take it here and it's gonna be the same thing. This height is f of x. So, and dx is the thickness. So if I set this up, I can use this formula. V equals to the integral going from a to b 2 pi x f of x dx. Our f of x here is 2x squared minus x cubed. And so if you substitute, we have 2 pi x, the intersection point here, y equals to 0. Again, it's just the x-intercept of this function, the x-intercept of this function. So it's 0 and 2, it's right here and here. So it's going to be 2 pi x, and here we just have x because the axis of revolution is the y-axis times our function. Then it's a pretty simple integral. If you integrate that, again, you can multiply dx or distribute dx and then take the integral term by term. So you get x4 over 2 minus x to the 5th power over 5. Substitute and by 2 and by 0. And if you do all these calculations, you get 16 pi over 5. Basically, what we did, we found the volume of this solid, so which is shown. What we did, we piece here, we rotated it, found that the volume of that piece, and then just added all those volumes, and that's what we obtained. So that number is the volume of this object. Example 2 or B. Find the volume of the solid obtained by rotating about the y-axis, again, the region between y equals to x and y equals to x squared. Now, this one we have two functions. So we have, this is y equals to x squared, and that one is y equals to x. So basically, we are taking this solid and rotating that about the y-axis. So again, we can take a hollow shell here or a cylindrical shell by cutting it here and then rotating it. Let's see what we need. What we need first, this is the formula, 2 pi x f of x dx. Let's see what these are. Now here, x is just the distance from the y-axis to the middle of that rectangle. So this is our x. The height of the solid, we know, is the difference between these two functions. Y equals to x is the top one, and y equals to x squared is the bottom one. So it's the shell height, which is x minus x squared. And of course, we know we are rotating it about the y-axis. You can find the intersection points by putting the two functions equal to each other. And if you do that, you get 0 and 1. So the coordinates of this point 1 and 1. Now, if we write the integral, we have everything we need. Again, f of x in this case is not one function, it's that distance. So I can just say that equals to f of x here. And I wrote it here, let's set it up. So we go from 0, the integral, the volume is the integral going from 0 to 1, 2 pi. X doesn't change because it's that distance. And the height or the function is x minus x squared. So it's going to be 2 pi. We can take the 2 pi out. So the integral 0 to 1 x squared minus x cubed dx. You can evaluate the integral and substitute the limits, and that's, I think, pretty straightforward. And if you do that, you get pi over 6. Let's do this example. Find the volume of a solid obtained by rotating about the y-axis again, the region between these two functions. So now the first step, what I did, I tried to, this is a simple parabola. You can graph that. So you can, if you want to use calculus, find the derivative, put it equal to 0. That's going to give you the x value of the vertex. You can substitute back and get the y value of the vertex. So the coordinates of the vertex are 2 and 4. You can find the intercepts, factor out x and put equal to 0, so it's 0 and 4. Basically, if you graph this function, we have this parabola. So it just goes down. Then y equals to x is the 45-degree line passing through the origin. So that's y equals to x. So graph to the two functions. The next thing is find the intersection points. So take the first function, put equal to the second function, and if you solve that, you get 0 and 3. And these are the intersection points. Here and here. Basically, this is our solid. And we want to take this and revolve it about the y-axis. So if I take again a shell here, so in 2 dimensions, it looks like a rectangle. So we are kind of revolving that rectangle. You can see. So what do we need? We need x, which is the radius. So that's from the axis of the revolution, which is the y-axis, and I put that here. Let's call those x, y, to the middle of this rectangle. So that doesn't change, it's x. We need the height of that rectangle, almost rectangle. So again, but the height is just the difference of two functions. So I called it h, and that's going to be, or f of x. We always use f of x. In this case, it's going to be 4x minus x squared minus x, and that's 3x minus x squared. We have the intersection points. So we know that the volume is going from a to b, 2 pi x f of x dx. So again, here it's going to be 2 pi x and our f of x, the difference of the two functions. The rest is a simple integral and substituting the limits, and of course we go from 0 to 3. So if you evaluate that integral, you get distribute, first take the 2 pi out, factor it, and then find the integral. So you get x cubed minus x4 over 4, substitute the limits, and your answer will be 27 pi over 2. Here they simplify. Now, next one is a little bit different, so pay attention to this one. Find the volume of the solid obtained by rotating about x equals to 1. So this is not the x-axis or the y-axis, it's x equals to 1. The region between 4x minus x squared and y equals to 3. Same thing. Try to graph this function, the first function, and it's the same function we just graphed. So you can take the derivative, put equal to 0, and you get the the x value of the vertex, substitute, and you get the y value of the vertex. Find the intercepts by factoring it and setting it equal to 0, so you get 0, 4. So basically, that's our function. It's a parabola. The other function is y equals to 3, and it's that line. This is our solid. So what we want to do is revolve that. Be careful, not about the y-axis, but about x equals to 1. So x equals to 1 is this line. So this distance from here to here is 1, and I can probably put that for you so you can see. So that's 1. Now, what's our goal? Our goal is to find the radius. What is the radius? The radius is from the middle of the rectangle to the axis of revolution. So as you notice, this distance is always x. From the middle of the rectangle to the y-axis is x, but what we should do is take that 1 out, because we only need that distance, not the whole thing. So this is our radius here, and that's x minus 1. And the height, again, is right here. The height is going to be f of x, which is the top function, minus the bottom function is 4x minus x squared minus 3. Setting up the integral. So here I found the intersection points. You put two functions equal to each other, you solve for x, and you get x equals to 1 and x equals to 3. The volume, again, in this case, you can write is 2 pi times radius times height and times dx, because again, we are revolving it at x equals to 1, which is parallel to y-axis. If the axis of revolution is parallel to the y-axis, then you put dx here. If the axis of revolution is parallel to the x-axis, then this is going to change to dy. And again, the limits change. But let's go over this. We need the radius. The radius, we got it here. Draw the function, the solid, and easily find those numbers. So it's x minus 1. The height, so we found that too. So this is the height, which is the difference of the two functions. So you substitute, and let's see, the limits of the integral, they go from 1 to 3. So these are the limits which we found it by finding the x values of the intersection point. The rest is just factoring, taking 2 pi out, and you get that easy function to integrate. You take the integral of each term and you substitute the limits. And if you do that, you get 8 pi over 3. I think that's good enough for this lecture. Now in the next lecture, I'm gonna do some examples when you're revolving it about the x-axis, or about y equals to a number, which is very similar once you understand the concept. All right, now you're ready to try some problems. Thank you for watching and have a great one, everyone. I'll see you in my next recording.